This video is part of an online course on algebra and will be about the minimal polynomial. In the last video, we studied a bit about eigenvalues and eigenvectors and their relevance in making the matrix of a linear operator very simple, that is, more precisely making it diagonal. Now, we have given a necessary and sufficient condition for there to exist a basis under which the linear transformation becomes diagonal. The condition is there must exist a basis of eigenvectors. Now, you can find these eigenvectors only when you know the eigenvalues, and I did not give you any way of computing the eigenvalues. I had hinted about the use of the characteristic polynomial, which we cannot really define at this stage fully simply because I have not introduced the determinant yet. You might be familiar with the basic properties of determinant from school, but we have not formally introduced it in this course, and we will not formally introduce it in this course. So the characteristic polynomial is technically not available to us. Furthermore, even if the characteristic polynomial was available to you, it gives you only an illusion that you can compute the eigenvalues. Simply because I do not know any person who actually remembers the solution to a cubic equation from the top of their head. So forget about higher degree equations for reasons that have to do with Galois theory. You cannot even find a simple expression for the solution of a fifth degree equation, for instance. In any case, we need to develop the theory behind finding the diagonal form at least, even if it's practically not that relevant. So for the first thing we need to do is, how do you find the eigenvalues? Well, we can encode the eigenvalues as the roots of a polynomial, not the characteristic polynomial, which we do not have the technology to develop, but the roots of a different polynomial. How does that work? Well, let's set the stage. We have an operator, and suppose lambda is an eigenvalue with corresponding eigenvector v. Then by definition, TV is lambda v. Now take any polynomial over the base field f. We know how to evaluate a polynomial on an operator. That gives P of t. What is P of TV? Please pause the video and work this out. It's not going to take you more than a couple of minutes. So please pause the video and try to figure out what the action of the polynomial evaluated on t, v is. I hope you got this. It's a rather straightforward computation. Write out the polynomial as a n z power n plus dot 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 a naught. Then by definition, P of TV is, in the place of z, you just chuck in t. So you get a n t power n plus dot 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 a1 t plus a naught identity is v. Let me recall again, t power n just means t composed with itself n times. Okay. Now, repeatedly using the fact that TV equal to lambda v immediately gives you that t power nv is actually lambda power nv. This is completely trivial. You can, if you are the pedantic type, you can prove this by induction, but it's completely trivial. Okay. So these composed operators also have v as an eigenvector, but the eigenvalue changes. The eigenvalue of t power n becomes lambda power n. Remember, v is non-zero by assumption. So v would be an eigenvector for the operator tn with eigenvalue lambda power n. Okay. Now evaluating P of tv, we get an lambda power nv plus an minus 1 lambda power n minus 1 v plus dot 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 a1 v plus a naught v. Okay. Now we can factor v out, and you get P of TV is actually just P of lambda v. That worked out to be nice, and you can do this factoring because after all we have all the common algebraic things that you can do hold in a vector space. Associativity, commutativity, distributivity, you mix all of these together, you get P of TV equal to P of lambda v. Now what does this tell you? Because, so what's the crucial observation? Well, the crucial observation is if P of t is 0, in this case we give an extremely powerful name. We say that the polynomial P is an annihilating polynomial of T. Okay, if P of T happens to be 0, then P is said to be an annihilating polynomial, or we use really what do you say, warfare language, we say P annihilates T. Okay, so if P annihilates T, then P of T V has to be 0, because P of T is 0, which is equal to P of lambda V. But V is not 0, because V is an eigenvector and we do not allow eigenvectors to be 0. The only conclusion that we can get, the only possible way that this can all happen, is if P of lambda is 0. Okay, so the crucial observation to take away from this brief computation is any annihilating polynomial of T must also annihilate the eigenvector V. Okay, by which what I mean is P of lambda V must be 0. Okay, that's what I mean by the annihilating polynomial must also annihilate the eigenvector V, which means any eigenvalue is the root of every annihilating polynomial. If you have a polynomial which destroys T, P of T is 0, then if lambda is an eigenvalue, P of lambda has to be 0. So we can encode, or rather we can, every single annihilating polynomial has within it as roots the various eigenvalues. This is what we want to grab on. We want to figure out these eigenvalues. We want to extract them in some way. Okay. Amongst all the annihilating polynomials, there is a very special one called the minimal polynomial. What's the minimal polynomial? Well, let's say, take a definition. Let T from V to V be a linear operator on a finite dimensional vector space. This is extremely crucial. Let A be the collection of all annihilating polynomials. That is, it's all the polynomials over the base field in one variable that destroys T. That is P of T equal to 0. So A is the set of annihilating polynomials. It's so much fun to say the word annihilate. So A is the set of annihilating polynomials. Then in this set, there is a unique polynomial m of z, which is called the minimal polynomial, whose leading coefficient is 1. What does that mean? If the degree of m is n, then the coefficient of z power n in the polynomial is 1. Okay, that's what the leading coefficient means. That means this coefficient an, this is 1. Okay, then we say, in fact, in this scenario, we say if the leading coefficient is 1, leading coefficient of a polynomial is 1, we say P is monic, M-O-N-I-C. It's a monic polynomial. Okay. Okay, so what is this saying? Then there is a unique polynomial which is monic, such that every element in the annihilating set is a multiple of m of z. Okay, the polynomial m of z is called the minimal polynomial. Why is it called the minimal polynomial? Well, for obvious reasons. It's sort of the polynomial with the lowest degree, because it divides every other polynomial in A. Furthermore, the degree of m of z is less than or equal to dimension of V. The degree of the minimal polynomial is not too large, it's at the max the dimension of V. So let me repeat, what is this result saying? It is saying that first of all, there is an annihilating polynomial. That itself is not clear, right? Why is this set non-empty? It could be the case that no polynomial destroys T. So first of all, this result says that the set of polynomials that annihilate T is non-empty. Second of all, it says there is a unique polynomial whose leading coefficient is 1. There is a unique monic polynomial such that every polynomial in this annihilating set is a multiple of m of z. It's a multiple of the minimal polynomial. And finally, it is saying that the degree is less than or equal to dimension of V. Okay. So the fact that the dimension, the degree of the minimal polynomial is less than or equal to the degree of v is not that important, at least for our purposes. So what I'm going to do is, I'm going to first give a quick proof why there exists at least one annihilating polynomial. Then I'm going to erase that proof and then give the proof that there is, the rest of the results. I'm going to give two proofs of the fact that there is an annihilating polynomial. Actually, both proofs are essentially the same, but one of the key ideas you will repeatedly see in linear algebra, so I want to do it twice. Okay, so this is a quick and slick proof that there is a polynomial that destroys t. What you do is, you look at identity t squared t cube t power n squared, where n is the dimension of v. Okay, look at identity t squared t cube t power n squared, where n is the dimension of v. Okay, then this is a collection of n squared plus 1 linear operators, or this is a list, that is a better term. This is a list of n squared plus 1 linear operators on LV, right? In LV, that is better. Now, what am I going to say next? You don't have to be a telepath to figure that out. You just have to be following the logic. So please pause the video and figure out what's going to come next. I hope you got it. There is a non-trivial linear relation amongst these n plus 1 operators. Why? Why is there a non-trivial relation? Well, if n is dimension of equal to dimension of v, then L of v is also a vector space over the base field f of dimension n squared. And here is a list of n squared plus 1 elements of L of v. Therefore, it's got to be linearly dependent. Therefore, there is a linear relation amongst these n plus 1 operators. Now, what does that tell you? It tells you that C0 I plus C1t plus C2 t squared plus Cn squared Tn squared is identically 0. It's the identically 0 operator which is also sitting inside LV as the additive identity. Now this immediately tells you that if you take the polynomial p of z to be equal to C0 plus C1 z plus C2 z squared plus Cn squared z power n squared, this is a polynomial that annihilates t, as we have just demonstrated. That's how the coefficients were chosen. So p is there in the set A. Okay, so this is the argument that shows that there is at least one annihilating polynomial. Now I'm not going to I'm going to erase this proof. This is just a quick proof. This idea keeps occurring again and again in linear algebra. Try to find some sort of polynomial. You take these operators, iterate them, and try to find a linear relation by considering sufficiently many iterations. Okay. Now I'm going to reprove this whole thing again in a slightly different way, because I want to get the dimension conclusion. Here I do get a dimension conclusion. I get that the dimension, or sorry, the degree, I want to get a degree conclusion. The degree of the minimal polynomial is at the max n squared. That's what this is going to tell you. But I want to get dimension of v for completely reasons of what do you say, completeness. It gives you a bit of understanding. So what I'm going to do is I'm going to completely erase this page, or maybe I'll not erase this page because I need it for future reference for you. So let me give the full proof again. The logic is going to be the same. The logic is going to be exactly the same, but I need to get the dimension conclusion. The degree of the minimal polynomial is at the max dimension of V. Okay, how does that go? Well, I do the same argument, except this time I start with u not equal to 0 in V. Take an element in the vector space V which is not 0. Now you pull the same trick. You consider this list of vectors u, tu, dot dot dot, t power nu. Okay. This is a list of vectors in V, and recall n is dimension of V. Now for exactly the same reasons, because this list, the length of this list exceeds the dimension of V, there is a linear relation. You have C0 u plus C1 tu plus dot 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 Cn t power nu is 0. This is because this is a list whose length exceeds the dimension, and therefore you must have linear dependence. Okay. Now what you do is you call the polynomial q of z to be C0 plus C1z plus dot 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 Cn z power n. Okay. And the conclusion from our discussion so far is q of t destroys u. Okay. Q of t u equal to 0. Now, it is by no means obvious that q of t is going to be 0. All this discussion says is that q of t kills u. It might not kill every single vector in V. If it kills every single vector in V, then q kills t itself, and therefore q is an annihilating polynomial. But unfortunately, the deficiency of this line of argumentation is that we get only that q of t equal to 0. Okay. Now, what are we going to do? Well, let's think about this. When are we done? Well, if dimension of V happen to be 1, if dimension of V happens to be 1, then we are actually done, right? For trivial reasons, because there is only one vector in the basis, and you just choose that vector and do this argument. You get in fact you will get a linear polynomial. You will get a linear polynomial that kills the operator t, right? So if dimension V equal to 1, we are done. We are done. Okay. So assume by induction, or we will prove this by induction. We will now apply induction on n, which is the dimension. Induction on n. So assume the result is true for all vector spaces and all linear operators where the underlying vector space V has dimension less than n. Then the claim is it's also true when the dimension is exactly equal to n. The base case is what we have just seen. Okay. Okay. Now how does this help us? How does this help us? Well, look at range. Look at range of q of t. Look at range of q of t. Now, first of all, observe that because q of t kills V, it also kills tu, t squared u, dot 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 t power nu. Why is that? We know that I wrote q of t kills V. That is going to be highly misleading. It kills u. Since q of t kills u, it also kills tu, t squared u, dot 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 t power nu. Why is that? Any ideas? I hope you got it. It's simply because if you take q of t and do t power nu, you can switch it around. This is the same as t power n q of tu. This is simply because of the fact that polynomial multiplication is commutative. Because polynomial multiplication is commutative, you can, whenever you do q power t into t power n u, you can just switch it around and say it's t power n into q power t u, q of t into t power n into composed with q of t u, and t power n composed with q of t u is actually 0 because q of t u is 0. So this is 0. Okay, this is 0. Now we can also assume, I want to say, okay, so what you do is we make a slight change. See, the way I have constructed q, you are going all the way up to n, right? You're going all the way up to n, but it can be the case that you get linear dependence well before you go to t power n u. The first line of the proof merely says that if you go up till t power n u, then you're guaranteed to get linear dependence. But it could be the case that you already got linear independence much before you reached n, right? Much before you reach, and that's quite possible. For instance, you could be in the kernel, in which case t of u is already 0, right? So you could have gotten linear independence long before. So what I'm going to do is, I'm going to make a slight change. I'm going to make this n into m. I'm going to make this n into little m. Okay, here also little m, here also little m. Okay, and I'm just going to say for some minimal m which is less than or equal to n. That is, choose the lowest number possible such that when you take the list u, tu, t power mu, you get linear relation. That is, the smallest m such that the list of vectors u, tu, t power mu is linearly dependent. Choose that m. What we have really shown is there exists an m and this m is less than or equal to n. That's what we have shown. Okay. Rest of the proof is there is no modification. I have to here change it till m. Okay. Now, so here also I'll just make it k. So that things are clear. So q of t will kill tu, t squared u, t power mu. Okay. Now, if you think about it for a second, you will conclude that the dimension of the span of u, tu, t power mu. If you look at the dimension of this span of these list of vectors, this dimension is exactly equal to m. Okay. This is because we chose that minimal m such that this list is linearly dependent. Okay. So the dimension of the span of u, tu, t power mu is exactly equal to m. Okay. What is this trying to say? Combined with the fact that q of t kills tu, t squared u, t power mu, it also kills u. That's how q was in fact selected. What we can conclude is the dimension of the null space of q of t is greater than or equal to m. Okay, because it kills this entire list of vectors u, tu, t power mu, and the span of this has dimension exactly equal to m. By the way, m was chosen to be that minimal number that makes this list linearly dependent. Okay, that was a lot of argumentation. If you are confused or stuck, you can always use the digital features of rewind or slowing down the video. Watch this bit again. It's a subtle bit of argumentation. Okay. So we have shown that dimension of null q of t is greater than or equal to m. Now that means by rank nullity theorem, the dimension of the range Q of t is less than or equal to n minus m. Okay. So the dimension of the range is less than or equal to n minus m. Okay. How does this help? Well, by induction hypothesis, we know that there is a polynomial, let's call it R of t, R of z, such that R of t annihilates, R of t is 0. Why am I complicating it? I have notation. Okay, not R of t is 0, that is wrong. R of t restricted to range of Q of t is 0. Why is that? Well, first of all, we already saw that if you take a polynomial and you consider the null space and the range of the polynomial evaluated on t, both are actually invariant subspaces. In fact, that's the reason why we even consider evaluating polynomials on operators. If you take an operator, plug it into a polynomial, you get another operator, and the original operator is invariant on both the image and the null space of the evaluated operator. So range of Q of t is actually an invariant subspace of t, and the dimension of the range of Q of t is strictly less than n, simply because m is at least 1, because we chose u to be non-zero. Therefore, you can find a polynomial such that t restricted to range of qt gets destroyed, right, by R. This is just by induction. This is by the induction hypothesis. We are inducting on the dimension, remember that. Induction hypothesis. Okay. Now, what does this tell us? Well, observe that the original vector space V is actually range Q of t direct sum null space of Q of t. The original vector space V is actually range Q of t direct sum null Q of t. How does this help? Well, let's think about this. If you look at the new polynomial, which is P of z, by definition to be Q of z times R of z. If you consider this new polynomial, which is Q of z times R of z, in fact, I don't even think I need the fact. Okay, let's talk about the direct sum later. Even without the direct sum, I can make some interesting conclusion. Let's look at the new polynomial, which is P of z, which is equal to Q of z times R of z, and consider what P of t of any vector v is. Okay, look at P of t of any vector v. Well, this, by the properties of polynomial multiplication, this is going to be R of t, I'm switching things around, R of t times Q of t v. Okay, it's going to be R of t composed with Q of t times v. But Q of t v is obviously in the range of Q of t for trivial reasons, and R of t kills range of Q of t. That's how R was chosen, right? R of t here, that's how R was chosen. R of t kills range of Q of t, so this is 0. This is 0. Okay, this is 0. So net conclusion is P kills T. We have found an annihilating polynomial of T. Now, all that remains to be shown is that degree of P is less than or equal to n. That was one of the claims that I made, why I need to go through the second argument. If you just wanted a polynomial that kills t, the original argument that I gave 2 pages ago that just deals with the linear dependence on the space L of V, that is sufficient. But I have claimed that you have degree of p is less than or equal to 1 n. Now I have run out of space. Let me see if I can create a new page. Here it is. Here is the place to add new page. Yeah, thank you. So I have added a new page. Let's continue the proof. We have to show that degree of p is less than or equal to n. Okay. Now what do we know? We already know that degree of q is, what was the degree of q? It was, let me just see, degree of q was m. Degree of q was exactly m. Degree of q was exactly m. And we also have dimension of range of q of t is less than or equal to n minus m. This is less than or equal to n minus m. Why do we have that? Well, that's just by rank nullity. It's here. I have argued that already. Now, by induction hypothesis, we actually have degree of R is less than or equal to n minus m. Okay. We have the degree of R is less than or equal to n minus m because when you are applying induction, let's not just make the induction hypothesis that there is a polynomial that destroys the operator t. We can use the induction hypothesis, there is a polynomial that destroys t and whose degree is less than or equal to the dimension. We can make that the induction hypothesis and conclude that the degree of R is less than or equal to m. So this together gives the conclusion that degree of P is less than or equal to m plus n minus m, which is equal to n. So I don't even need this direct sum claim. This is not even needed. Okay. So we have found a polynomial whose degree is at the most n that kills the space A. Okay. Now that is not the full statement. We want to show that there is a unique polynomial whose leading coefficient is 1 and such that every other annihilating polynomial is a multiple of m of z. Well, that's not so hard. What we will do is we will yet again add another page. I drastically underestimated the length of this proof. First of all, so let us consider A. What we have really shown is A is not empty, right? Recall A was the set of all annihilating polynomials of T. This long argument shows that A is non-empty. Now what I am going to do is let m of z be the polynomial with least degree in A. Consider the polynomial with lowest degree in A. Well, this obviously exists. There must be a polynomial of lowest degree. We can assume M is monic. Why can we assume M is monic? Well, for stupid reasons, we can just divide by the leading coefficient and make the leading coefficient 1. Remember, the polynomials are over a field, so inverse elements exist for the scalars, right? So we can assume that M is monic. We want to show that this M is unique. We also want to show that M divides every other polynomial in A. So let P be in A. Let P be in A. Now the argument is essentially just division algorithm. By division algorithm, I'm going to abuse notation and reintroduce Q and R, but now they will mean something entirely else. This is something that you have to get used to in mathematics proofs. Now that that part of the proof is over, I am free to reuse the same variable names yet again, right? So by division algorithm, I can write M as, in fact, I have reintroduced P also. P was the polynomial that we used right here, but that part of the proof is complete, so I am going to reuse letters. So M, or rather P, I can write as MQ plus R with degree of R less than degree of M. This is just by the division algorithm for polynomials, which we have shown earlier in the course. Now, by hypothesis, P of t is 0, M of t is 0, therefore M of t into Q of t is 0. So we conclude R of t is 0, because R of t is just P of t minus M of t composed with Q of t, and M of t is 0, so you can switch things around, so you will get that R of t is 0, but degree of R is less than degree of M. So the only conclusion possible is R is 0. R has got to be the 0 polynomial. And because R is a 0 polynomial, we have concluded that P is a product of M and Q, which is what the claim was. Every polynomial that annihilates T must be divisible by M. And of course, you still have to show that there is unique monic polynomial. That is rather simple. If M1 is another monic polynomial of least degree, that kills T, then just consider M minus M1, and I'm not going to even elaborate. You will get a simple nonsensical conclusion. Therefore, M has got to be equal to M1. Okay? So, we have completed this long and somewhat tedious proof that there exists a polynomial that annihilates T, provided the space is finite dimensional. If you take the leading coefficient to be 1 and look at the least degree polynomial, that is going to be unique, and that's going to be the minimal polynomial, in the sense that every other polynomial that kills T is divisible by M. Okay. So we have shown the existence and uniqueness of the minimal polynomial. Okay. Now this next fact is why the minimal polynomial is so useful. We already know that because any annihilating polynomial has roots, as within its roots the various eigenvalues. That's what prompted the discussion of considering annihilating polynomials. If a polynomial annihilates an operator, it also annihilates each eigenvalue, right? But the minimal polynomial is special in the sense that the roots of the minimal polynomial are exactly the eigenvalues, no more, no less. There are no other roots of the minimal polynomial apart from the eigenvalues. Let T from V to B be a linear operator on a finite dimensional vector space, and let M of Z be the minimal polynomial of T. If lambda is a root of M of Z, then lambda is an eigenvalue of T. Now the next part is just the fundamental theorem of algebra, so I will not even elaborate the next part much. Furthermore, if V is a complex vector space, then the minimal polynomial has the form m of z equal to z minus lambda 1 power k1, z minus lambda 2 power k2, z minus lambda r power kr, where lambda 1 to lambda r are the distinct eigenvalues of t and k1 to kr are positive integers. And the final conclusion is what makes complex vector spaces so important and so nice. Operators on complex vector spaces always have eigenvalues. Why? Because there is a minimal polynomial, and the minimal polynomial can be factored like this. Okay, we will see the proof that complex vector spaces always have eigenvalues from this when we prove this now. Okay, how are we going to prove this? Well, we already know one direction. If you have an eigenvalue, it is going to be a root of the minimal polynomial. That's what started the discussion. So suppose lambda is a root. Suppose q of lambda or m of lambda is 0. We have to show that lambda is an eigenvalue. Why is that so? Well, if lambda is a root, if m of lambda is 0, you can write m of z as z minus lambda times some other polynomial q of z. Right? This is just basic high school factorization. Whenever the polynomial has a root, you can take z minus lambda outside. I think we have even shown this in this course. Anyway, it's completely trivial. It's just an application of the division algorithm. So m of z is z minus lambda times q of z. Now apply t. So m of t is t minus lambda I q of t, which in turn equals 0 because m is an annihilating polynomial. It kills t. Therefore, t minus lambda I times q of t equal to 0. The proof is actually complete, and it's complete for a very, very clever reason. Well, degree of q is less than degree of m because I have factored out one of the monomials, right? So the degree of q must be less than degree of m, which means q cannot be an annihilating polynomial because the annihilating polynomials are all divisible by m, or alternatively m is the lowest degree possible annihilating polynomial. So any polynomial of even lower degree cannot possibly annihilate t. So degree of q has to be less than degree of m, which means q is not an annihilating polynomial. So q is not annihilating, which means there exists v in v such that q of tv is not 0. Okay, there exists a v such that q of tv is not 0. Let's call this q of tv as u. So what does this equation tell us? Well, this tells us that t minus lambda I of u is 0. And we also know u is not 0. Right? U is not 0, which means lambda is an eigenvalue. Lambda is an eigenvalue with eigenvector u. Okay, so this also proves the next part about complex vector spaces. If you have a complex vector space, then you can always factor out m of z as z minus lambda 1 par k1, z minus lambda 2 par k2 dot 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 z minus lambda r par kr by the fundamental theorem of algebra. Now, because lambda 1 to lambda r will be distinct eigenvalues, will be the eigenvalues by the first part, complex vector spaces always have eigenvalues. This is what makes complex vector spaces much better behaved than real vector spaces. Okay. Now, coming back to how exactly do I find the eigenvalues? Well, if you find the minimal polynomial, maybe there is some hope that you can find the eigenvalues. How do you find the minimal polynomial? Well, there is no exact method available to you currently, but you can use a heuristic. What's a heuristic? A heuristic is a method that works most of the time. Something you can take it like a heuristic argument means it's not perfectly rigorous, but it might work practically. So here is a practical algorithm for finding the minimal polynomial. We just follow the proof. What you do is you pick a vector v. Of course, v should not be 0. Pick a vector v not equal to 0 and look at v squared dot 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 t power dimension vv. Okay, this is linearly independent. Okay, and there exists non-zero scalars such that a naught v plus a1 t power v plus dot 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 a n t power n v equal to 0. Now, theoretically, there is no reason to expect that you need to go all the way till n. Maybe the linear dependence occurs much before. In fact, we used this reasoning in the proof. We chose an m and that m, all we can say is less than or equal to n. But for empirical reasons, by which I mean that if you experiment out with various operators, you can just start with R3 and consider some randomly generate operators which are just 3 cross 3 matrices. It will turn out that greater than 99% of the cases, this is what I mean by for empirical reasons, for reasons from observation. For empirical reasons, it happens that the above equation has a unique solution when with an equal to 1. Now what does that mean? The only way by which this equation has a unique solution with an equal to 1 is if the minimal linear relationship amongst this list of vectors occur only after you consider the n vectors or the n plus 1 vectors. Okay. The only way by which this has a unique solution is if no previous subset or no previous sublist is already linearly dependent. If some previous list was linearly dependent, then you can find multiple solutions for this equation, right? You can find multiple solutions for the equation. Please pause the video and think about why this is the case, okay? Because for experimental reasons, it turns out that there is a unique solution with an equal to 1. If you think about what that means is the minimal polynomial has to be of degree n. That's what it means. So typically what this is saying is in 99% of the cases, it happens that the minimal polynomial is of degree n. Now once you know this, that the minimal polynomial is of degree n, you can reverse engineer and find out the minimal polynomial. How do you do that? You fix a basis. Once you fix a basis, V becomes just column matrix, T power n just becomes a n cross n matrix. So does T squared dot dot dot, they all become n cross n matrices. So you will have a huge system of linear equations. This whole thing becomes a huge system of linear equations where the unknowns are the unknowns are the coefficients a0 to an, right? You get a huge system of equations in a0 to an. You have to find a0 to an such that this whole thing becomes 0. You know the operator t, therefore you know the matrix of the operator t. You know v, in fact you picked v, so you know the coordinates of v. When you multiply this out and add everything, you get a huge bunch of system of equations. You can solve that system and you get a solution a0 to an. You get a solution a0 to an, and you get a unique solution because, as I said, for empirical reasons you get a unique solution. Then you look at a0 I plus a1t plus a2t squared plus dot 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 t power n is 0. Then this polynomial a0 plus a1z plus dot 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 z power n has no choice but to be the minimal polynomial of t. Why is it that it has to be the minimal polynomial of t? Because this equation happens to have a unique solution for an equal to 1, and recall that the minimal polynomial is that monic polynomial which destroys the operator t. Therefore, it must destroy t of v as well. And because there is only one solution for this, it has to come from the minimal polynomial, because the minimal polynomial is also unique. The minimal polynomial is the unique monic polynomial that destroys t. There is only one set of coefficient that allows you to destroy this v, t, v, this list of vectors. There's only one set of scalars that give you a linear relation with an equal to 1. Therefore, you are forced to conclude that this has got to be the minimal polynomial of t. Okay. And as I said, this is not a rigorous proof. This is just empirical evidence. If you have been asked to compute the minimal polynomial, if you randomly choose the vector v, you are most likely going to get the minimal polynomial. Okay. Let's take an example illustrating this. Okay. For practical reasons, the example has to be doctored. Since the matrix M here is rather huge, it's actually a 5 cross 5 matrix, bunch of coefficients have to be 0, otherwise the computations are going to get hairy. Now we are going to try to find out the minimal polynomial. The matrix here is this. So set v equal to e1 in the preceding argument, take v equal to e1, that's the simplest one. Then you notice that t of v is u2, t squared v is e3, t cube v is e4, t power 4 v is e5, and t power 5 v is minus 3e1 plus 6e2. This is just a straightforward computation. Just check this. This is completely trivial from the matrix. Okay. And now looking at this for some time, you will be able to conclude that t power 5v minus 6 t power 4v plus 3v equal to 0. Okay. And also notice that v, tv, t squared v, t cube v, t power 4v are linearly independent, and therefore no previous list is actually going to vanish. No linear combination of the previous list is going to vanish. So the minimal polynomial has to be of degree 5, and you have found one polynomial that that kills tv. And therefore, the minimal polynomial, by the reasoning that I gave in the last slide, has to be z power 5 minus 6z plus 3. No choice. No choice. Okay. So notice the key reason is why there, we want a unique solution for this equation with an equal to 1. That just says that this vector is there in the span of the preceding vectors. In this case, the vector which is minus 3e1 plus 6e2 is there in the span of the preceding vectors. That's what we need. Okay. But that happens in a unique way because the first 5 vectors are linearly independent, and therefore if the sixth vector is in the span of the first 5 vectors, the span, there's a unique linear combination of the first 5 vectors which gives you the sixth vector. Okay. So this allows us to conclude that z power 5 minus 6z plus 3 is the minimal polynomial of t. Okay. Now let's think about this example a little bit more. We have found the minimal polynomial. Can we find the eigenvalues? Well, the operator corresponding to the matrix, as you can see, is just this. That's again completely trivial to see. This is the operator from, let's say, f5 to itself. The minimal polynomial is given by this, and it's a 5th degree equation. And as I said, from Galois theory, there is no way to write down the roots of this polynomial in some simple expression or formula that involves radicals. By radicals, what do I mean? I mean taking roots, cube roots, 4th root, 5th roots of the various coefficients. If you recall, the solution for a quadratic is minus b plus or minus root of b squared minus 4ac by 2a. This is actually an algebraic expression that involves the square root operator on the coefficients, right? So it's a combination of the coefficients with some square roots, division, etc. happening. You cannot find such a simple formula in general for higher degree equations. Now it is possible that for some special collection of polynomials of high degree you have a formula, but in general there is no formula, and that follows from Galois theory. Okay. So the net conclusion is the theory that we have so far developed is completely practically useless unless we doctor the operator. By which I mean, for examination purposes, you come up with an operator in which the eigenvalues are somewhat guessable. That is why I don't like introducing the characteristic polynomial at this stage. The minimal polynomial, though difficult to compute, is much more valuable as a theoretical tool than the characteristic polynomial, as we will see. Okay. Now suppose I know the eigenvalues. Suppose I know the eigenvalues, then what happens? Okay, suppose I know the eigenvalues, what happens? Then you can compute the eigenspaces. So start with an operator in F3 given by T of ABC is BC0. You're sort of doing a left shift. You're doing a left shift. You can figure out very quickly that the only eigenvalue of T is 0. That's very easy to check. And it is also very clear that the minimal polynomial is ZQ. Okay, so I reiterate, this means the only eigenvalue is 0 and the corresponding eigenspace is the collection which makes T ABC 0, which is clearly just the subspace A00, and the dimension of this subspace is 1. So there is only, if you look at a basis for E0, there is only one vector in it, and therefore you cannot get a basis consisting of eigenvectors. Thus, you cannot represent T as a diagonal matrix under any choice of basis. So, as we have seen, even simple operators, T ABC equal to BC0, it's a very simple operator. It is not diagonalizable simply because there is not enough eigenvalues. So, the obstruction is not just practical. You might think that the only obstruction in diagonalizing a operator is the lack of a method to find the eigenvalues. Here the eigenvalues is clear by inspection, the eigenspace is also clear by inspection, and you simply cannot diagonalize this. Okay. The last example gives us a very obvious sufficient condition for diagonalizability. If you take an operator from V to V on a finite dimensional vector space, if you have dimension V distinct eigenvalues, if you had dimension V distinct eigenvalues, then we can find a basis of V consisting of eigenvectors of T. That is, if you had distinct eigenvalues and you had enough of them, then corresponding to each eigenvalue, you have at least one eigenvector. In fact, you have exactly the dimension of each eigenspace will have to be 1. No choice. Think about why that is true. Okay. So, essentially the proof of this is the dimension of each eigenspace is 1. The dimension of each eigenspace has to be 1, and since there are dimension V distinct eigenvalues, you choose a basis for each one of these eigenspaces, which will consist of exactly one vector. You put them together, you get a list of dimension V linearly independent vectors, and that has to be a basis for the space V, and therefore T can be represented as a diagonal matrix. So this is a trivial criteria. It's an obvious sufficient criteria. It is most probably useless because in most scenarios you won't have distinct eigenvalues. So here is a doctored example. Consider T from R2 to R2 given by T of xy equal to yx. The matrix of T with respect to the standard basis is 0, 1, 1, 0. Okay, and by inspection you can figure out that the eigenvalues are 1 and minus 1. This is completely trivial. You just play around with this matrix for maybe 7 minutes. You will be able to figure out that the eigenvalues are 1 and minus 1. Thus, T can be represented by a diagonal matrix under a suitable choice of basis, right? Because you have found two distinct eigenvalues. So, by the obvious sufficient criteria, this operator is diagonalizable. Okay. Now, here is an interesting theoretical fact about the minimal polynomial that is going to prove to be extremely useful in applications. Suppose you have a finite dimensional vector space T from V to V and you have a T invariant subspace W. That means when you restrict T to W, you get an operator. Then the minimal polynomial of the restriction divides the minimal polynomial of T. Okay, the minimal polynomial of the restriction divides the minimal polynomial of the main operator t. Why is this the case? Well, this is because the set, if you take the set, the annihilating set of t restricted to w, then the minimal polynomial of t is there. T destroys the entire operator t, m, the minimal polynomial of t destroys the entire operator t on the whole space V. So in particular, m destroys t restricted to w as well. This is completely trivial. It is true just by definition. Therefore, the minimal polynomial of t is there in the annihilating set of t restricted to w, but every single polynomial that is there in the annihilating set of t restricted to w is a multiple of the minimal polynomial of t restricted to w, which is just another way of saying the minimal polynomial of the restriction divides the minimal polynomial of t. Okay. Let's see another example of a non-diagonalizable operator. These are operators on Fn. It's a matrix. The matrix, for reasons that has got to do with my lack of latex skills, it's slightly confusing. On the diagonal, you have lambdas. Okay, it's an n cross n matrix. On the diagonals, you just have a lambda, single lambda. Right above the diagonal, you have ones. Right above the diagonal, you have ones. Everywhere else, it's a 0. Everywhere else, it's a 0. Such a thing is called a Jordan block. It's called a Jordan block, and we will become well acquainted with Jordan blocks in the final week when we show the existence of the Jordan canonical form and work out a few examples. So this is called a Jordan block. This is a operator on Fn. Now, the only eigenvalue of this Jordan block is lambda. Can you pause the video and figure out why this is the case, that the only eigenvalue is lambda? I hope you figured out this case, why the only eigenvalue is lambda. Well, to really see that, if you take another lambda 1, then what is j minus lambda 1 I? What is, maybe I have added a space for justification, maybe I should do it here. So look at j minus lambda 1 I. What is that going to look like? Well, it's going to look like almost the same thing, except on the diagonal it's going to be lambda minus lambda 1 dot 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 lambda minus lambda 1, and here you have 1 1 1 and everywhere else 0. This is how j minus lambda 1 I is going to look like. Now recall that the restatement of lambda 1 being an eigenvalue is the fact that the null space of j minus lambda 1 I is non-trivial. So this should have a non-trivial null space. Now let's think about it. When will the null space of this matrix be non-trivial? Well, if the range, when you apply this to V, some column vector V, you should get 0 and V should be non-zero. When is that going to happen? Well, when you multiply this matrix by another column matrix V, what you're really doing is taking a linear combination of the columns. So some linear combination of the columns should be 0. Okay, some linear combination of the columns should be 0. But it is completely clear, that the columns are linearly independent unless lambda equal to lambda 1. That's just clear by inspection again. Yeah, or you could sit down and waste your time writing a rigorous proof if you're not satisfied. But by inspection, it's clear that the columns of this matrix are linearly independent. And therefore, the null space of j minus lambda 1 I is trivial unless lambda happens to be lambda 1. If lambda happens to be lambda 1, the first column is 0 and you get linear dependence trivially. Okay, so the only possible eigenvalue of the Jordan block is lambda equal to lambda 1. Now what is the eigenspace corresponding to this? Well, when you do this lambda minus lambda 1 and set lambda 1 equal to lambda, which is the eigenvalue, the matrix you get is zeros everywhere, and you have a bunch of ones. Right? Now if you think about it, this is nothing but sort of like a 0 vector in the first column. The second columns, third columns are like u, e2, e3 dot 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 up until e1, e2 dot 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 up until en minus 1. This is what the other columns are like, right? After having subtracted lambda I from j, the diagonals become 0, and above, this entire thing becomes 0. I have a nicer picture so I can illustrate with that. This becomes 0. So you have e1, e2 dot 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 en minus 1. Okay, so when you multiply j minus lambda I with a vector v and you expect it to be lambda v, then what happens? Well, if you think about what happens, you get, let me just think for a second. When you multiply it out, you get C1 times first column plus C2 E1 plus dot 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 C, also should be C, Cn En minus 1 equals 0. Okay, so when you do j minus lambda I times v, where v is C1 to Cn, you get a linear combination of the columns of j minus lambda I, and that's just going to be C2 E1 plus dot 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 Cn En minus 1 equal to 0. But this is linearly independent, so that means C2 to Cn has to be 0. So the eigenspace will be anything in the first coordinate, it doesn't matter, anything in the first coordinate, a0, 0, 0, that would give you all the possible eigenvectors corresponding to the eigenvalue lambda. So the eigenspace is a0, 0, 0, this subspace, and therefore the dimension of this is 1, which is far less than dimension of v, which is n. Therefore you cannot find a basis consisting of eigenvectors. Thus these Jordan blocks are not diagonalizable, for again the same reasons. You have to have enough eigenvectors to form a basis. Okay. Finally, one trivial fact that relates invertibility and the minimal polynomial. If you have an operator on a finite dimensional vector space, then that operator is invertible if and only if the constant term of the minimal polynomial is non-zero. If and only if the constant term of the minimal polynomial is non-zero, is the operator diagonalizable, invertible. Well, this is completely trivial because T is invertible if and only if null space of T is trivial, if and only if 0 is not an eigenvalue, if and only if the minimal polynomial as non-constant, constant term non-zero, that is better, has constant term 0. Okay, so the operator T is invertible if and only if the null space is trivial, if and only if 0 is not an eigenvalue, if and only if the minimal has constant term 0. Think about each one of these if and only if conditions. There are 3 of them, all 3 of them are completely trivial. Once you figure out what these 3 if and only if conditions, why they are true, you will be convinced that an operator is invertible if and only if the minimal polynomial the non-constant term is, the constant term is non-zero. So that was a lot of material about the minimal polynomial. Since we spent a lot of effort proving that a minimal polynomial exists, we will see plenty of applications in the next video. We have already seen one application, the fact that whenever you have a complex vector space, then there are non-trivial eigenvalues and eigenvectors. That followed from the fact that minimal polynomial factors into linear factors. That's the fundamental theorem of algebra. So that concludes this video. This is a course on algebra and you have just watched the video on the minimal polynomial.